different formulas. So here we have a spring in the relaxed position extended by 0.4 meters. We have to figure out the work done by the spring. So we will start with the formula itself. Work done by the spring will be initial minus final, like we discussed earlier. And the formula for elastic potential energy we know is half kx square. Now, initially, the spring was in the relaxed position, which means we can write the value of x is equal to 0. So, the spring is neither compressed nor it is stretched. So, we can say that the initial elastic potential energy will be 0. Finally, the spring has been extended by 0.4 meters. So, we can use the value of x as 0.4 meters. So, here we go. Initial potential energy is 0 since the spring is in the relaxed position. Finally, we use half kx square, k is 48 and x is 0.4. And then we just subtract initial minus final. So we'll get 0 minus 3.84, which comes out as negative 3.84 joules. Hence, we can say work done by the spring will be negative 3.84 joules. Now, the same question we had done a while ago, where we found the elastic potential energy. There we found the elastic potential energy was positive 3.84 joules. So if you analyze the work done by the spring and elastic potential energy stored in the spring are having different signs. One will be negative and the other one is positive. Here we have a spring that obeys the Hooke's law. It is stretched by a distance x and stores energy E. What is the work done by the spring when it returns to the point where x is reduced to half of its original value? Now, since we have to figure out the work done by the spring, we know the formula is initial energy minus the final energy. And the formula for elastic potential energy we know is half kx square. So initially they have given the energy is E. So let's write it down. Initially the energy is E. The distance, the stretching distance is x. So we write down half kx square. In the final situation, x reduces to half of its original value. So final energy, let us write EF, that will be equal to half k. The value of x will be x by 2 squared. Now, if we simplify this, we'll get half kx square and then we'll have a 4 in the denominator. Now, half kx square is nothing but E. So, the final energy we can write is E upon 4. Now, according to the formula for work done by the spring, we have to subtract both energies, keeping initial in the first place. So, let us write the work done by the spring will be equal to the initial energy, which is E, minus the final energy, which is E by 4. And if we simplify this, we will get 3E by 4 as our answer, which means option C is correct for this question. Okay, this is a graph-based question. We have been given a graph. X-axis is the force and the y-axis is displacement. The elastic potential energy stored in the spring is E when the extension is E. We have to figure out the work done by the force on the spring to increase the extension to 3E. So step number 1, please identify, do we have to find the work done on the spring or by the spring? So let's see. We have to figure out the work done but on the spring. So let me underline this, work done on the spring. Accordingly, our formula will change. So work done on the spring, we'll write final energy minus initial energy, where the energy is half kx square. Now, initially it is mentioned that the energy is E. So let us write it down. E will be equal to half kx square, but in this case, x is E since the extension is E. So we will write half k E square. Finally, let us write down EF. Let's say EF stands for the final elastic potential energy. So we will write half k and the new extension is 3E. So in the brackets, we will write 3E whole squared. So this comes out as half k E square and we have a 3 square which is 9. Since half k E square is equal to E, which means we can write the final energy can be written as 9E. Now let us apply the formula final energy minus initial energy. So we'll write 9E minus E. So let's write down. Work done by the spring will be 9E minus E, which comes out as 8E. And hence option C is the right answer for this question. Next, here we have a spring of K value 200. It is compressed by 6 centimeters. At the point where the box has moved 4 centimeters, how much work has done by the spring? So like always, we have to figure out the right expression for the work done. Since the work done, we have to find by the spring. Hence, the formula will be initial energy minus final energy. So let's solve. So consider this as case 1 when the box is in this position and the spring has been compressed by 6 centimeters. Case 2, when the box has moved by certain distance. So analyze this. Let's say this red line represents the position of the box in case 1 and this red line represents the box in the case 2. So it is mentioned in the question that the box has moved to the right hand side by 4 centimeters as I have shown here. So we can say that like in case 1, you can see the compression in the spring is 6 centimeters. So initial compression is 6. But what will be the final compression? If you recall, compression is the distance of the box from the relaxed position. That's why we said initial compression was 6 centimeters. In case 2, when the box has moved some distance, so the distance of the box from the relaxed position, this arrow will represent the final compression. So that will be 6 minus 4, which will give us 2 centimeters as the final compression in the spring. Now the work done by the spring, the formula is initial energy minus final energy. Initial energy will be half kx squared, and let's put all the values in. The value for k as given in the question was 200 and the value of compression 6 centimeters. So we convert that into meters first. And if we solve this, we will get 0.36 joules as the initial elastic potential energy stored in the spring. Finally, the formula stays the same, but the only difference is the value of x. The final compression in the spring was 2 centimeters. So if we convert that into meters and use it, we will get 0.04 joules as the answer. After finding out these two energies, we use the expression work done by the spring will be initial minus final. So it will become 0.36 minus 0.04, which comes out as 0.32 joules. So coming back to the question, option C is the right answer for this question. Here it is mentioned that an object of mass 0.78 kilograms attached to a spring of unstretched length 560 millimeters. So let's draw a diagram. So watch. We have a vertical spring of unstretched length 560 millimeters. This means 560 millimeters is the natural length of the spring, where we can say the spring is neither compressed nor it is stretched. Hence, we can say that the force on the spring in this position will be equal to 0. So this is the relaxed position of the spring. Now analyze. If we put a box of mass 0.78 kilograms and attach it to the spring is of course going to extend. And the new length of the spring is given as 620 millimeters. So let's analyze this in a diagram. So here we have the box of mass 0.78 kilograms. Because of the weight of the object, the spring has been extended and the new length of the spring is 620 millimeters. Now we have to figure out the total energy stored in the spring as a result of this extension. So the formula for energy, elastic potential energy, is given by half kx squared. First of all, the value of k is not given here. So we need to do something to figure out the value of k. And also we need the final extension in the spring. So how do we figure that out? Let's analyze. So in case 2, when the box was kept, the total length of the spring was 620 meters. And initially, the length was 560 meters. Hence, we can say if we subtract these two lengths, that will give us the total extension in the spring. Hence, we can write extension x will be equal to 620 minus 560, which comes out as 60 millimeters, which can be converted into meters like this, because while using the formula, we have to take the value of x in SI units. So x we have found. Now the value of k, the spring constant, is clearly not given. So how do we figure that out? For that, we have to use this information. It is saying when the object has come to rest. From this information, we can deduce that if the object is at rest, then the net force acting on the object will be equal to 0. Next step would be to identify what are the different forces acting on this object. The first is, of course, the weight of the object, which is mg acting downwards. And then we have a spring force. Now, the spring force is either pulling or pushing, depending on whether the spring has been extended or compressed. So in this case, the spring has clearly been extended. So the spring is going to pull the object upwards. So let's analyze this. So we will represent the Fs is the spring force pointing upwards. Now, since we have deduced that the net force on this object will be zero, hence the spring force and mg will have to balance each other out. So let's write Fs will be equal to the weight of the object. Spring force by Hooke's law is kx, which will be equal to mg. Now, if we make k as the subject and try to put all the values in, the value of x, the extension we had figured out was 0.06, mass is given as 0.78, and the value of g is 9.8. Now, if we simplify this, we will get the value of k as 127.4 newtons per meter. Now, we have the values of both parameters, k as well as x. So let's write down the formula half kx square, and the value will be half. K is